Alright, half adder versus full adder. So from previous video, this is what we look at as a half adder. So what it does is, you got two bits that you're trying to add. Each one of them is one bit wide. The result is one bit wide. The carry is one bit wide as well. So you take two 1-bit number, add them, produce a sum bit and also a carry bit. But this is not very useful. Let me show you why it's not useful, because it doesn't have a carry. Let me show you by giving you a simple decimal example. Let's say 782 plus 228. Okay, if you add this number, 2 plus 8, you have a 0. You got a carry in to the next digit. 821, that's 11. You got a carry out. Okay, 721, 10, 0. You got a carry out. So if you look at this particular stage, right? If you look at this particular stage, this is your carry in. This right here is the carry out. Okay, our half adder is not capable of taking in a carry in, produce a carry out, and a sum bit. So we have in this case, our x and y, if you think about it, is 8 and 2, and the sum bit is 1, carry in is 1, and carry out is 1. But our half adder is not capable of doing that. So for it to be more generous purpose like this, what we need is actually a full adder. It's capable of generating a carry, sum. They're actually 1 bit. It's capable of taking an x, capable of taking a y, the second number, and ability to produce. Also taking a c in, and we're going to relabel this as c out. So how do we design the logics? How do we design the logic that goes in here? What is the logic that go in the box? So if you look at it, C in, X, Y, C out, and S, we have, what we basically have is, we have 3 input. With 3 input, C out and S. Okay, with 3 input, we basically have 8 cases. Oops. We basically have 8 cases that we're dealing with. So this is separation, so we'll make sure that we won't make any reference error, and then completing them. Okay. So adding those number, 0, all 3 0, answer is 0, carry is 0. Answer is 1, carry is 0. Answer is 1 as well, carry is 0. Answer is 0, carry is 1. 0, 1. So what it means is, when you add 1, 0, 1. When you add 1, 0, 1, your sum is 0, carry is 1. Because if you add 1 plus 0 plus 1, you get 1, 0. 1, 0 here is 1, and 1, 1. So with this, what you could do is put it in K-map. Put in K-map. Let's say this is the C out, C in, X and Y. You gotta pay attention. We kind of treated C in as the most significant bit. So it's because it's on the most left side of our truth table. Okay, so so what we have is 0, 0, 0, 1, 1, 1, 1, 1. Okay, and for S, we have this. So C in 0, 1, 1, 0, 1, 1, and 0, 1, 1, 0. I'm just taking straight from the table. 0, 0, 0, 1. Okay. Once we have that, you could start writing equation for it. Oop. I think I might have created a mistake right there. That should be 1, 0, which means that I need to get this corrected. That should be 0, and there should be a 1 here. Okay. So now we can write C out equal to, so it's actually this. This is the best you could do. So it will be C in Y, C in X, and XY. And for this, for S, there's really not much simplification that you could do. Okay, so it's C in X, Y, not C in not X not Y, C in X, Y, and C in X. Okay, so this is the logic that goes in here. Okay, the beauty of this is now we can do this. Now that we can do A plus B, if A is equal to A3, A3, A2, A1, and A0, B is B3, B2, B1, and B0, right? What you could do is you could use 4 of what we just built before, okay, and then we just tie this to 0 because there's nothing coming in. There's no carry in for the first stage. Tie all of it together. This is the C. So A1, A2, A3, B3, B2, and B1. Okay, and that is sum 0, sum 1, sum 2, and sum 3. This is carry 1. So this is C0 equal to 0, C2, C3, and C4. Okay, and each one is a full adder. So this is how you can use a basic component, a 1-bit full adder that we built, and put together a 4-bit adder. Okay, so